Welcome to the next video in the Discrete Math video series. This is video 20, talking about truth functional satisfiability. So to start with a definition, we define a proposition to be satisfiable if there exists some choice of truth values that we could assign to the propositional variables such that the result, after combining it with the logical operations, is a true proposition. So any proposition which has such an assignment that makes it true is called satisfiable. So just for a quick demonstration, let's consider the proposition P or Q and not R, and we will show that this proposition is a satisfiable proposition. By the way, note that a proposition is not satisfiable means the same thing as it being a contradiction. A proposition is satisfiable if it is either a tautology or a contingency. Anyway, continuing with this example, let's look at the truth value assignment, assigning P to true, Q to true, R to true, and recall that because we are using the binding precedence, then the conjunction binds more tightly, and so we evaluate it first. I'll use parentheses here to express that we are computing the conjunction before the disjunction, and also the negation binds more tightly than anything, but since that's at the end, that didn't really need saying, but in any case. With this assignment, we see that we get true or true and false. The true and false turns into false, and the true or false turns into true. Since this assignment of truth values made the sentence true, therefore it is satisfiable. So to show that something is satisfiable, you simply provide some assignment to the variables, which results in the entire proposition being true. Now, when it comes to that, there isn't a whole lot to exercise, and therefore I don't feel like I'm quite in a position to write down an exercise. Let's just somewhat abruptly switch topics, as the book does, and say that just as a matter of notation, we sometimes need to write down long conjunctions, which would just be saying, you know, this proposition is true, and this one is true, and this one is true, and so on. So sometimes we need long contradictions, and sometimes we need conjunctions. And sometimes we need long disjunctions. And so as a matter of notation, rather than just writing down a whole lot, we're going to invent a certain notation that allows us to compactly write down conjunctions and disjunctions of arbitrary length. And so you see here where I have this big upward wedge with a subscript I equal 1 and a superscript 1001. Next to that, I write P sub I. That's a conjunction of all of the propositions P1 to P1001. And then here you see this disjunction, which I chose to give kind of a funny, weird number up as the upper bound, but just to kind of demonstrate that you can, with this notation, write down disjunctions that have very long length. And so next we're going to do an exercise where I want you to find a proposition which is true when P and Q are true and R is false. So it should be true in that scenario. But in every other scenario, the proposition should be false. So here you see, right? I want the whole thing to be true when P is true, Q is true, and R is false, right? So when those three variables have those three values, I want the entire proposition to be true. In every other case, the entire proposition should be false. Okay, that's problem one. For problem two, I want to write down a proposition using our new and special notation, which asserts for a 9x9 Sudoku problem that every cell of the 9x9 grid contains a number from 1 to 9.